In the last video, we introduced Laplace transforms. Now we want to look at Laplace circuits or circuit analysis in the complex frequency domain. So we had some transforms that we gave in a table where we had these zero conditions, and these zero conditions are a little bit confusing. We also forgot to include one transform in the table, so we'll just note that one for now. But going back to the zero conditions, what are they? What even goes in there? Well, they are initial conditions of the system. So what that means is that we need to know something about the original system. Otherwise, we're kind of just forced to assume that they're equal to zero. And this is where a little bit of that confusion comes in, where we have zero from the left versus zero for these values. And if we can assume quote unquote nice functions, which as engineers is often the case, then we can make these substitutions for zero from the left and zero. And as engineers, this is one of the many ways that we may upset mathematicians or physicists, something that we have to just accept and move forward from. So from the properties of Laplace transforms, we can say that the Laplace transform of one function f and another function g, if they're summed together, they're going to be equal to the summed together transforms. So we have this linearity that's pretty nice. And this is great for KVL and KCL. So as far as the order of events for how to analyze a Laplace circuit, first, we want to collect some information in the time domain. So that could be those zero state conditions or whatever may be relevant. Then we want to transform everything into the S domain or the complex frequency domain. And that allows our differential equation to become an algebraic equation. From that algebraic equation, we solve for current, voltage, power, anything we want really. And then we can transform back into the time domain. Now, while this may seem a little bit cumbersome, it's going to be a lot easier than the differential equation, especially if you have a complex system. So collecting the info on the system is probably given to you, or you know what that is. Usually not too much work to figure out what that is. In the last video, we looked at how to transform things into the S domain. We're going to get into that a little bit more. So we're going to introduce something called an impedance, which we're all used to, but except now it's going to be in the S domain, and it's given as the voltage divided by the current in the S domain as the units of ohms. Nothing real special there. We also introduce a parameter called the admittance, which is the inverse of the impedance, which is equal to the current divided by the voltage in the S domain. And I don't think the admittance has been introduced in any of the courses so far, so just take note of what it is and the units. So we want to consider an inductor. We know that the voltage over an inductor is equal to the inductance times the time derivative of the current. We can transform that into the S domain and say that the voltage is equal to S times L times the current. So we transform that, and then we get the inductance times this initial condition. And this kind of looks like a KVL a little bit. So we would say that VL is quote unquote our voltage source. S times L is our impedance. I is our current. And then we have this term here. It's kind of odd because it's not really an impedance, but because we're kind of considering this a KVL, we're going to call it some pseudo voltage source. So if we look in the time domain, how we would express a inductor and the voltage over it, we have this here. We're all commonly used to that. But looking at it in the complex frequency domain, we now say that the voltage over this entire system is equal to this current times this impedance, and then we have that pseudo voltage source there. So this is where we differ a little bit from that phasor transform, because we get this zero state condition here. But if it's equal to zero, it looks fairly familiar. And now if we consider a capacitor, where we had the displacement current equal to the capacitance times the differential of the voltage, can transform that into the S domain to arrive at this equation here. What we're going to do is divide everything by CS, simply that we get another KVL looking equation where we have the voltage source, the impedance 1 over SC, the current, and it should not be a current source. Neither of those should actually be current sources. That's a little typo. And then we also get this pseudo voltage again. We have 1 over S times V naught. So looking in the time domain, we would express a capacitor like this, but in the complex frequency domain, we get that additional voltage source or pseudo voltage source looking component in there. So when we transform our circuits, we have to pay attention to those initial conditions because otherwise we model our circuit wrong. And in the next video, we'll actually start modeling circuits and do some analysis and see how simple things can actually be.